Today we are talking about quantum advantage. Specifically, we'll be discussing what quantum advantage should look like and how recent developments have played into our understanding of it. So really the focus is going to be on, as you can probably guess, the recent Nature cover paper put out by, in part, a team at IBM. It's called Evidence for the Utility of Quantum Computing Before Fault Tolerance. I will, of course, link the paper below. So this has been, I guess it's a little died down now, but this was very much all the rage a couple weeks, months ago. I don't know how time passes. And we're just going to be chatting basically about what quantum advantage is and what this paper means for it. This is going to be a pretty short video. And when I say quantum advantage, by the way, quantum utility, it's the same thing to me. So in this paper, the authors argue that their 127 qubit experiments, in which they simulate this time evolution of some 2D transverse field Ising model, give evidence of quantum utility because they show that you can solve a problem that is very difficult to solve using MPS, which is matrix product states, or certain 2D tensor network methods. So that's basically the thesis. You can see, that's just like literally what they say in their abstract as well. So as we go through it, you can just see their hardware setup. This was on some Eagle chip, I assume. I don't know if they say which one, Kiev maybe. Kiev. And then we have a nice set of figures here showing how error mitigation is essential to the success of this operation. Of course, if you've paid attention to any of IBM's marketing, you'll notice that the continuous path to quantum advantage is a big phrase they have, which emphasizes that error mitigation will provide a continuous path, I guess, to quantum advantage, and that it will not be a simple binary, oh, we have fault-tolerant quantum computing, now we can do very useful things. Before that, we could do nothing of use. Whether that is true remains to be seen, but that is just for context, a common claim. And so in this paper, I won't review the technicals of it. Of course, you can read it for yourself. I find it to be pretty accessible. They argue that, there is a benefit here. There's an advantage to using a quantum computer because you can do this computation more efficiently than you could on a classical device. Now, of course, worth noting is that advantage can mean many things. Here they call it utility, but you can have speed, you can have energy, you can have computational cost. There's a lot of ways to get advantage that is often lost on the community, on the science community, right? From a business perspective, even if something is the same amount of time, but it's cheaper, like, okay, I'd want to do that. Or if it costs less energy to run a data center, right? Like, these are very financial motivations, not computational at all, which is, no one ever, or very few people talk about in the science community. But when it comes to providing a quantum advantage, real quantum advantage would be a big watershed moment for the quantum computing industry. And to be honest, I'm not sure if this is that moment. Now, before we talk about this paper anymore and some reactions to it, let's go back in time, perhaps. You might be thinking, quantum advantage in 2023, didn't we have quantum supremacy in like 2018, 2019? This seems like a regression. Quantum advantage is sort of a lower bar, perhaps, in quantum supremacy. And we had quantum supremacy like 5 years ago, right? Like, that's a fair question, I think, to ask. And the short answer, I guess, is that we didn't really have quantum supremacy, or if we did, then I think quantum supremacy is a useless goal. On a terminology note, I've always disliked the term quantum supremacy because it's very ill-defined to me. Supremacy is sort of traditionally defined as quantum computers doing something that's intractable. on a classical computer, which is complexity-wise, everything's tractable on a classical computer. Like it by definition has to have some pragmatic connection, because it's not just like supremacy isn't just doing an algorithm with an exponential speed up on a quantum computer. It's actually doing a algorithm that would be very slow, and so on a classical computer. So I could run like a 5-qubit Shor's algorithm and say that's exponentially faster, but that's not supremacy, right? And so because it's not really a strictly complexity-based definition, it's really based on a very empirical, pragmatic argument on what a quantum computer can do, that the notion of intractability is entirely unclear. For example, in the original Google paper, they claimed it would take 10,000 years to simulate their system on a supercomputer. And now it's like, who gets to decide what intractable is? 10,000 years? What if it was 1 year? What if it was 10 months? There's no real definition of intractable. It's kind of wishy-washy. Of course, even 10,000 years was immediately disputed. I'll link that paper below. And even if the 10,000 years were true, it places sort of a temporal restriction on supremacy, i.e. supremacy is a thing that can be changed. It would seem like, oh, we have quantum supremacy. Next year, we're still going to have quantum supremacy, but that may not be the case if classical computers sufficiently accelerate, or algorithms sufficiently accelerate, as we've seen with Google's experiment. It's been simulated I don't know, there's been a bunch of different groups that have done it on GPUs. And so I don't think you could honestly claim that paper is supremacy at all at this point. I'm not even sure if you can claim it's advantage, because although you can do it faster, you can achieve way better fidelity using these crazy tensor network methods on GPUs. So I not even sure if it's quantum advantage, much less quantum supremacy. But even if it was, ignoring everything I've said so far, even if it was 100% undisputable, indisputable, whatever, quantum supremacy, it's still like, who cares? Because the simulating random circuits is kind of like a useless task for the most part. And the whole supremacy is just basically a large quantum advantage, is all it's defined as. So using quantum advantage seems like a better term, because it's strictly like greater than, less than, not greater than by some arbitrary amount. But even if we did have supremacy, right, is like, does that mean anything? In 2019 and in 2023, those chips are basically useless. Like the 53 qubit Sycamore chip then and now, from any commercial or scientific perspective, is, I don't know, like mostly, if not entirely, irrelevant. And so the supremacy experiments, right, we're asking a question: which is better at being a noisy quantum circuit, a classical computer or a noisy quantum circuit? So it's like, obviously a noisy quantum circuit is going to be better. For this line of questioning or challenging, I'll refer you to this video by this, I don't know, Fields Medal mathematician, really smart guy, on the quantum teapot test. It's an interesting concept, but we don't need to talk about supremacy anymore. Basically, I took the long way around to say that if we did have supremacy, it doesn't matter, but we also didn't have supremacy. So back to this IBM situation and the paper that IBM put out, in addition to other colleagues, is this quantum advantage, right? The watershed moment where we can do something interesting. Now, I saw a lot of criticism of this. Now, I think the pendulum, right, has swung in the other direction scientifically. For a while, scientists, investors, are like, C-suite executives, like, they're not worth people worth listening to on anything. But when it comes to like the actual scientific community, there was a fair amount of bullishness for a little while, which has now sort of swung the other way. Now it's like, before it was like hip to be, everyone was, the mainstream opinion was oh, quantum circuits are so good, or NISQ is going to be so good. So like the contrarian cool perspective was be, no, NISQ sucks, right? But now that's sort of the mainstream opinion. So I don't know. I don't know if that makes NISQ is cool, the hip new opinion, but like criticizing NISQ is kind of played out. I mean, like everyone does that. No one has any original ideas there. So there's a lot of that, right? Like IBM released this into the wild, but the wild has certainly, like the tides have turned on scientific favorability on NISQ. There was a lot of very valid criticisms, some of which I will leverage, but there's also a lot of random criticisms. Ironically, the first two papers I saw on this, on like responding to this paper, so a bunch of groups, right, put out papers saying, oh wait, we can actually simulate this efficiently, so you don't have quantum advantage. That's like the argument a bunch of groups did. Ironically, the first two papers I saw, I don't know if they were actually the first published, but one of them was by the authors of the ridiculous Grover's algorithm paper, which last I checked actually is still not retracted. I don't know how that's still up there, but that I've actually covered, or I talked about in a previous video. It's kind of a meme now in the community. And so, that's funny. And the other one was a Google PR piece, which of course, irony there from the company that, famously claims supremacy, and, definitely this IBM paper, I don't know if it was really advantage, but it's a lot closer to advantage than Google has ever been to supremacy. So at least they have that going for them. But the question is really, do we have quantum advantage? I think that the resounding consensus from the scientific community is pretty skeptical. But I'm sort of putting a claim more in the I don't know field, in the sense that, how can I claim that, right? There's like 30 different papers which we have that can claim to simulate the IBM results on like a laptop or GPU. So how could anyone reasonably say this is at all advantage? Now, beyond some crazy nitpicking of, time comparison on pulses and stuff, the key thing is that every one of these papers is an approximation. I mean, keep in mind that quantum is an approximation too, because you're using like Z&E is a biased estimator of the true expectation value. So there's, it's an approximation in itself. And so we're sort of comparing an approximation to an approximation, which is not like showing any provable correctness, right? Like I could give you like these papers, right? They compare to these experimental data, and they're like, look, it works on small systems. We scale it up to big systems. It matches the experimental data. Our approximation matches another approximation, which doesn't really indicate much to me. I could give you an algorithm. I could break the record for every single algorithm out there by orders of magnitude. I guarantee it. And my secret sauce would just be to write into memory the exact IBM results, and so we just get like however many CPU cycles that takes, and so it would look exactly the same, but obviously it's not. It's just right. It's a hard-coded algorithm. It's not even an algorithm maybe, and so that's not like right, like that. To evaluate an algorithm, you can't just run it and compare it to some other approximation and just hope that it works. I've even grown skeptical of these scaling up arguments, right? It works on small systems, so it works on big systems. Like I've seen that fail more times than I can count. So that's why I'm like, I don't know. Can we simulate this? We can simulate something very fast on these GPUs. Is it provably correct? Like, I don't think so. So I'm gonna go with I don't know if this is an advantage. I'm definitely skeptical, but this is one of the things I don't see a lot talked about. It. I think Jay Gambetta mentioned this some, and I'll link that discussion below. I honestly haven't seen any evidence one way or the other super compelling that this is or isn't some sort of quantum advantage. So while I remain skeptical that this is a watershed moment for the quantum computing community, it is somewhat exciting to me that this is even a debate, right? That is very exciting. So I think there's something there, and we'll see what error mitigation can do in the future, I guess. Some of the criticism, I'll just, as an aside, I'll link this below. An example I saw is that this is not an interesting problem. People are like, this is not a practical result. Or it's not a useful algorithm. And I agree and disagree in the sense that this is not this is not going to revolutionize some commercial industry, but at the same time, studying like icing models is people grind away on 1D, 2D icing models for whole PhDs running experiments. So like, this is a scientifically relevant problem. Like simulating icing models is an interesting problem to a scientific community. And really this is what I'm interested, like all these commercial applications are like whatever. People will make commercial applications out of anything, but it's really advancing science that's most interesting to me. And simulating IC models, I think, is a valid attempt or a valid way to do that. Much more interesting to me than random circuits. So yeah, that's just a few thoughts on the matter. I don't know if it's anything unique or interesting, but maybe it'll give a little bump to this discussion now that it's sort of died off since the paper came out a couple months ago.